Hello everyone, I am Subarna Datta. I have completed my BSc from University of Calcutta in 2005 to 2008. Then I have completed my MSc from University of Calcutta in 2008 to 2010. After that, I have done my PhD from SN Bose National Center for Basic Sciences in University of Calcutta in 2018. After that, I have done my postdoctorate degree from Shah Institute of Nuclear Physics from 2019 to 2021. I have applied for assistant professor in physics department of your institute. For that, I will talk about electromagnetic basic physics topic, that is electromagnetic theory, introduction to Maxwell's equation. Before going to Maxwell's equation, I will discuss about what is electromagnetic theory. It is the theory of electromagnetic field. Now the question comes into our mind, what is electromagnetic field? It is a combination of electric field and magnetic field. Suppose if the electromagnetic field is propagating along the x direction, that is the perpendicular to the electric field and magnetic field. So then the question arises how the electromagnetic field is generated. There is a Q charge that is oscillating along x direction, so electromagnetic field is generated, which is perpendicular to the electric field and magnetic field. And suppose there is a circuit and where there is a alternating current passing through this, so electromagnetic field is generated along the x direction, which is perpendicular to the E field, electric field and magnetic field. Electromagnetic field is associated with a wave field, wave type of kind of nature, so it associates with a wavelength. This is not a single type of wavelength, this is a multiple type of series of wavelength series. This is called electromagnetic spectrum, and that is the lower side of wavelength is gamma ray and the higher side is radio wave. To understand the basic theory of electromagnetic theory, we will talk about the Maxwell's equation. So what are those equations? Now I come to those equations. The first law is electrostatic Gauss's law. Suppose there is a charge or charge distribution Q and there is a closed Gaussian surface. So the total electric flux coming out is surface integral, closed surface integral E dot dA is equal to Q by epsilon naught. Epsilon naught is the permittivity of the in the free space. Q is the total charge enclosed by the surface. So according to the Gauss's divergence theorem, we know that the volume integral del dot divergence of electric field is equal to closed cyclic surface integral E dot n cap dA, and we know that the Q by epsilon naught, the charge distribution by epsilon naught is equal to rho by epsilon naught dV. Rho is the volume charge distribution. So according to combining these two equations, we will get the differential form of electrostatic Gauss's law, that is the divergence of electric field is equal to rho by epsilon naught. Rho is the volume charge density. Now we come to the Maxwell's second equation, that is the manostatic Gauss's law. Suppose there is a bar magnet and this is the south pole and this is the north pole. The magnetic field line, magnetic lines of force originates from the n side, north pole, and ends in the south pole. So the magnetic flux through any closed surface is always zero and the magnetic lines of force are always closed. So the closed cyclic surface integral of B dot ds is equal to 0. That is the integral form of manostatic Gauss's law. and according to the Gauss's divergence theorem, we will get that the divergence of magnetic field is always 0. This is the differential form of magnetic Gauss's law. So what is the significance of this second law? From this second law, we can say that the magnetic field is a solenoidal vector field and isolated magnetic monopole does not exist. This is the significance of the second law. Now I will come to the third law. This is the Faraday's induction law. What is that? We can say that from this law we can say that we know that the negative rate of change of magnetic flux, that is minus d phi dt, is equal to induced EMF. What is that? Suppose there is a circuit and if the magnet moved inside the coil, then a induced EMF is generated and a current is generated. So the galvanometer deflects, and if the magnet moved outside from coil, then the galvanometer deflects on the opposite side, and the rate of change of magnetic flux always opposes the induced EMF. So there is a negative sign arises. So now the integral form of Faraday's law is equal to closed cyclic integral E dot dl is equal to minus ddt of open surface integral B dot n cap dA. We apply the Stokes theorem, and from that we know that the closed cyclic integral E dot dl is equal to curl of E dot n cap dA open surface integral, and equating these two equations we will get that curl of E is equal to minus del B del T. This is the differential form of Faraday's law of induction. Why it is del del T? Because the volume, the area here, we have assumed that the area is constant, and we will partially differentiate with respect to time with the magnetic field, only the magnetic field B. So that is why it is del del T of B. Now we come to the fourth law of Maxwell's law, that is the Ampere's law. So what is Ampere's law? We know that if a current is passing through a circuit, there is a magnetic field induces, and the line integral of magnetic field around any closed path is equal to the mu0 times the total current enclosed by the path. That is the closed cyclic integral B dot dl is equal to mu0 I enclosed in the circuit. So applying the Stokes law, we can say that the open surface integral curl of B ds is equal to mu0 J dot open surface integral J dot ds. J is the total current density. What is that? Suppose there is a cylindrical circuit, and if a current I passing through the cylindrical rod, if we consider an Amperian loop C, so the total current density J is flowing into the rod, and using these two equations we can say that curl of magnetic field is equal to mu0 J, total current density. This is the differential form of Ampere's law. However, it is valid for magnetic field of steady currents, and in general it requires modification if the current changes with respect to time. So what is that? Here Maxwell modifies the fourth law. Before Maxwell, this is the four equations, and these are the four equations, and in the third equation, if we take the del dot curl E, so the left hand side is always 0 because the divergence of any vector del dot curl of any vector is 0, and if we take del dot minus del B del T, so according to the second law it is 0, that is consistent. But if we take del dot in the fourth equation, then the left side is 0, but the right side may not be 0. For steady current, the divergence of J is 0, but eventually when we get the not steady current, the current is changing with respect to time, then J is not current, J is not 0. So there must be there is the problem, and how we can solve this. For that, how Maxwell fixed this problem? So there is a circuit and there is a parallel plate capacitors, and it is connected with a battery. If a current I is IC, conduction current is passing through this plate. Suppose there is a flat surface and this is the Amperian loop, flat surface. So the closed cyclic integral B dot dl is equal to mu 0 I enclosed, that is the Ampere's law is valid. But there is a balloon shaped surface where there is no conduction current. So in this flat surface, the continuity equation, that the del dot J is equal to minus del rho del T, the equation of continuity equation is valid in the flat surface region. However, in the balloon shaped region, there is no conduction current. So it seems to be that the equation of continuity equation seems to be not valid. But it is not correct, because here we have to consider the capacitor. What is that? In this circuit, there is a battery and the capacitor is charging, accumulating charges, and the charges is accumulating. Suppose there is a Q by T and the charges is accumulating in the capacitor plate, and after a certain time it becomes all the charges accumulated and it becomes saturated. So in this transient region, the charge is changing with respect to time. That means the electric field is changing with respect to time. So we can write that cyclic integral B dot dl is equal to mu 0 I total. I total is IC, that is conduction current, and ID, that is the displacement current. IC is the conduction current, this is the conduction current, and in between these two capacitor plate we have introduced a new current component, that is the displacement current. So the electric field, we know that sigma by epsilon 0, and sigma is equal to Q by A. Q is the charge on the plate and A is the area. That is, the Q is the charge on the parallel plate and A is the area. And when the charge is accumulating in these two surfaces, that means the electric field is changing. So del E del T is equal to 1 by epsilon A dq dt, and we know dq dt is equal to I, that is the displacement current, ID. So we have modified the Ampere's law, that is the cyclic integral B dot dl is equal to mu 0 I enclosed plus mu 0 epsilon 0 integral del E del T dA. So if we choose the flat surface, here I is equal to I enclosed. But in this balloon shaped surface, there is I enclosed 0, but del E del T dA is equal to I by epsilon 0. So we get the same answer for either surface, and here the Ampere's law, modified Ampere's law, is valid. So in first case it is the conduction current, and the second, this is the displacement current in the balloon shaped region. So applying the Stokes law, we will get del cross B is equal to mu 0 JC plus mu 0 epsilon 0 del E del T. JC is the volume current density corresponding to the conduction current, and epsilon 0 del E del T is equal to the displacement current density. And from the continuity equation, we can also say that del dot G, if we divergence of JD is equal to minus del rho del T, as we have said already here, and minus del T of epsilon 0 del dot E, and from the first equation we will get that del dot epsilon 0 del E del T, which corresponds to this. So from the display continuity equation, the fourth law is also valid. So we have discussed in this lecture the basics of in electromagnetic theory and the fourth Maxwell's equation, basics of fourth Maxwell equations. Thank you for watching this video.